So heat transfers. What are the ways in which the heat transfers from one medium to another is basically what we are looking at here. And imagine you have a fire and there's a pan above the fire which has water in it with a handle. Now imagine you are touching this handle. The heat that you'll feel in your hand when you touch it is called conduction. So conduction is through direct contact. And the heat with which the water molecules at the bottom move forwards towards the surface is called convection. So convection is the transfer of heat through fluids like liquid or gas, all those are fluids. And whatever heat that you feel near the fire is your radiation. So those are the heats that are radiates towards its surrounding. That is radiation. And now whatever thermal quantities that we are going to talk about mainly has to deal with the conduction of heat transfer. Let us talk about the thermal quantities. There are four main thermal quantities. So you have thermal conductivity, thermal resistivity, thermal transmittance, and thermal resistance. Now let's start with thermal conductivity. So what does thermal conductivity mean? Thermal conductivity is the ability of a material to conduct heat, or the ability of a material to transfer heat. And this is denoted by K, and this is the ability of a material to conduct heat. And here the key word is material. Okay. So for a good conductor of heat, your K would be higher. And for a bad conductor of heat, your K would be lesser. So let's take an example. Let's consider copper and wood. Copper is a good conductor of heat. So your thermal conductivity or your K value would be higher. While wood is a bad conductor of heat, so your thermal conductivity or K value would be lower. So Fourier's law of thermal conduction helps in measuring the thermal conductivity of a material. So imagine you have a wall. And imagine a unit area in it. So this is your A. A is your unit area of the, we are considering let's say the wall. So in the unit area of a wall or any other building component. And this is your heat that passes through it, which is Q. So Q is your rate of flow of heat or your heat gain. And this rate of flow of heat per area depends upon certain factors. So your Q by A, which is rate of flow of heat per unit area, depends upon certain factors. And let's consider the factors first. So firstly depends upon the material, what material the surface is made up of, and the thickness of it. Like if it's a wall, then what is the thickness of the wall? And lastly, the temperature difference between the exterior and the interior surface. And let's try to understand the how all these three factors are related with your rate of flow of heat. Let's consider for each categories. Let's consider your thickness first, and this is your L. Temperature difference is delta T, and we'll talk about the material later. So your rate of flow of heat, let's consider not equal to, if the thickness of this material is larger, then what will happen to the rate of flow of heat? It will be lesser. So your rate of flow of heat is inversely proportional to the thickness of the wall. Okay, so this is inversely proportional. Now let us consider the temperature difference. So imagine this is your wall, and the temperature difference is higher. So what will happen to the rate of flow of heat per unit area? That will also increase. So your Q by A will also increase. And what does this mean? Your Q by A is directly proportional to delta T. Now, considering these two equations, you can say your rate of flow of heat per unit area is directly proportional to temperature difference by length of the surface or wall. So this is something that is taken from these two components of the factors that depend that the rate of flow of heat depends upon. Now let's consider the last thing, which is your material. So imagine you want to remove this proportionate sign and put an equal to it. So what would you do? You have to introduce a constant to the formula. So we'll write it as Q by A is equal to K into delta T by L. And this K is the thermal conductivity of the material. Okay, so I hope this is clear. And this is what the Fourier's law of thermal conduction also states. So a rate of flow of heat per unit area is equal to the thermal conductivity into the temperature difference divided by the thickness of the material. So from here you can take K as Q by A into L by delta T, right? And let's try to write the of measurement for thermal conductivity now. So we already know Q is your rate of flow of heat, which can be written as joules per second, or it can be written as watt. So it's either joules per second or watt. Then you have area, which is meter square. You have your thickness, which is in meters, and your temperature difference, which is degree Celsius. So this is basically watt by meter square into meter by degree Celsius. So you'll have 1 meter cancel. So the unit measurement of K is watt per meter degree Celsius. Or you can bring it above and write it as watt meter inverse 1 degree Celsius inverse 1. So this is the unit measurement of thermal conductivity. So now that thermal conductivity is clear, let's move on to thermal resistivity. And this is denoted as 1 by K. And by this itself, we can say thermal resistivity is nothing but the reciprocal of thermal conductivity. You can simply say it as reciprocal thermal conductivity. So what does that mean? It means the ability of a material to resist heat. And again, here the keyword is material. So what would be the unit of thermal resistivity? 1 by K is equal to, it would be the reciprocal of this. So you'll have meter degree Celsius per watt. Or again, it can be written as meter degree Celsius watt inverse 1. Let's move on to the next term of thermal quantities, which is your thermal transmittance. So thermal transmittance is usually found for building components. So this is the ability of a building component to transmit heat through it. And your building components could include walls or slab or window, all that such components. And thermal transmittance has two other name. With one is U value and the other is air to air transmittance. And this can be defined as the rate of flow of heat per unit area per temperature difference across the component. per unit area per temperature difference across the component. And with this itself, we can write the formula. So let's say U is equal to rate of flow of heat. Rate of flow of heat is your Q per unit area. So you have per unit area. So per unit area and per temperature difference. So per temperature difference. This is your U value formula. So U is your thermal transmittance or U value or add to watt transmittance. I'm just gonna write it as U value here. Q is your rate of flow of heat or your heat gain. A is your area and delta T is the temperature difference. And let's try to find the unit measurement of U value. So let's again try. U value is equal to rate of flow of heat. The unit is watts or meter per, joules per second. So watt divided by area is meter square. Delta T is degree Celsius. So your U value can be written as watt per meter square degree Celsius or watt meter inverse 2 into degree Celsius inverse 1. This is your thermal transmittance or U value. Now consider this formula again. U is equal to Q by A into delta T. And if you bring all these here, you'll get the heat gain formula, which is Q is equal to U into A into delta T. And this is your rate of flow of heat or heat gain formula. And this heat gain formula is basically of conduction, and whatever we are talking about is everything is through conduction. So this is conduction, and in the previous video I've talked about a heat gain formula where I've written Q is equal to the specific volumetric heat of air into volume of air into temperature difference. So this was for heat gain through convection, which is through fluid or air. And this is most not used in terms of finding the material or in our building structures. This is mostly for your fresh intake of air and mostly used for ventilation purposes. So that is not mostly used within our thermal quantities, and this is for thermal heat gain through conduction. This is through convection. So don't get confused. Both are the equation. This is for convection and this is for conduction. And mostly we'll use the conduction formula only. So mostly we'll use the conduction formula, which is this formula only. We'll mostly use in solving sums, and mostly it will what be asked in exams. So this is of more importance. About the last and final term, which is thermal resistance. This can be written as 1 by u or even r value. And again, as this suggests in its uh, in the first line itself, this is the reciprocal of thermal transmittance. So what does this mean? It is the ability of a building component to resist heat. So 1 by u can be written as, okay, before 1 by u, let's consider the u value. We know the formula for u is q by a into delta t. So what is 1 by u? 1 by u is a into delta t by q, and the unit of R value or thermal resistance would be meter square into degree Celsius by watt, which can also be written as meter square degree Celsius into watt inverse 1. So I hope all the four thermal quantities are clear. Now let's try to establish a relation between the thermal conductivity and the thermal transmittance. So what is the formula that we derived for thermal conductivity? Or like, okay, let's consider the Fourier's relation, Fourier's law, which is rate of flow of heat per unit area is equal to thermal conductivity of that material into temperature difference by the length of the material. This we know from the thermal Fourier's law of thermal conduction, or we can even take it from our thermal conductivity formula. Let's consider this one. And we know the U for value formula is U is equal to Q into A into delta T. And let's just consider this too. And you can consider 1 and 2. You get your Q by A into delta T is equal to K by L. Right? You're basically taking this delta T here and you get K by L. And this is nothing but your U. So U value can also be written as the thermal conductivity of the material by its thickness. Okay. Now let's move on to other set of formulas. So we saw the formula for U value, we saw the formula for K, and it's inverse for both. Now let's see the U value for a multi-layer component. What does this mean? So mostly you won't have a single layer material, right? You'll have your wall, you'll have plasters, and sometimes even a cladding. All those surfaces you'll have. So let us consider this is a wall section with plasters on either side and a cladding on the interior side. And let's consider each one. So let's consider the thickness of this to be L1, this to be L2, L3, and lastly L4. And let's consider the thermal conductivity of each material to be K1, K2, K3, and K4. So what would be the U value of this building component? Now, here's the thing, the U values cannot be added. So, U values are not added mathematically, or sorry, or arithmetically. So, what is that I'm trying to say is U value of this, say, wall cannot be U1 of the layer 1 plus U2 plus U3. It doesn't work this way because U values are not added arithmetically. But the reciprocal of U value, which is your R value, can be added arithmetically and so on. And your R is nothing but 1 by U. So your 1 by U1 plus 1 by U2 plus 1 by U3 can be added. Now here comes our the twist. So what you would do is when you're considering the u value of a component which has a multi-layer to it, you add something called as the surface conductance of the exterior and the interior surface. Now the each, okay, let's say you find the u value for this material. So we know the formula of u can be written as k by l. But if you find the K by L of this particular layer, it won't be the U value of that material. You'll call it as the thermal conductance of that material. So you won't call it as the thermal transmittance of that layer. You'll call it as the thermal conductance. So in a multi-layer component, each layer has its own thermal conductance, which is very similar to your thermal transmittance, but you just call it as conductance. And you add each conductance of the each conductance of the layer of the component. You add it together to get your U value of that component. So what you would do is you'll take 1 by u is equal to 1 by, and this is where I'm talking about the surface conductance. So you'll have the surface conductance of the outer surface plus your u values of the material, each layer. So 1 by u1 plus 1 by u2 plus 1 by u3 plus so on, you'll get like till 1 by un, and lastly you'll add it with your surface conductance of the inner material, sorry, inner layer. And this is the formula for a multi-layer surface. And lastly, remember to reciprocate to find the U value, because this still again is your thermal resistance. It's not your thermal transmittance. So what do? You find the value for this. You'll find something like 1 by something, and then you divide it, so you'll get something reciprocated basically, and you will find the U value of that material. Now we talked about multi-layer component. What about a multiple component in a single surface? So what does that mean? Let's see. So what does this mean? It's in a single surface. Say this is your wall. You have a door and a window. So you have multiple surface within a component. So how do you find the U value here? Now again, let's consider the area of the door to be A1 and the U value of the door to be U1, and the area of the window to be A2, U value to be A2, and the area of the wall excluding the door and the window, then that is A3, and the U value is U3. Remember, this is the U3 is the area, A3 is the area of the wall excluding the area of the door and the window. So this is this area alone. Then your u total u like of the surface would be u1 into a1 plus u2 into a2 plus u3 into a3 divided by a1 plus a2 plus a3, and this gets to add on to n number of surfaces. So this is the formula for finding the U value of a multi-surface component. So we saw the U value of multi-layered where you find 1 by U, which is thermal transmittance, and you in reciprocate it to find your U value towards the last. For multi-surface component, you just multiply the U value and the area of each surface, add it together, divide by the total area of each surface, and you'll find the U value of a multi-surface component. Now, let's move on to the other set of topics. Thermal damping. So, what does thermal damping mean? It means basically it tells you how well a building component or an envelope is resisting the outside temperature and the inside temperature fluctuation. Okay, resists the temperature fluctuations within the building, and it's usually expressed in percentage. And the formula for it is thermal damping is equal to the temperature range of the outside temperature minus the temperature range of the inner temperature of within the building divided by the outside temperature range into 100 because it's expressed in percentage. So TO is your outdoor or outside temperature range, and TI is your indoor or inner temperature range. Now let's talk about the sunpath diagram. All these concentric circles, each concentric circle, they represent your altitude angle. So what is altitude angle? Altitude angle can also be called as the sun elevation angle, and this is the angle between the horizon and the position of sun. So imagine you're standing here. This is your horizon, and let's say the sun is here. Then the angle between the sun and your horizon is the altitude angle or the sun elevation angle. Okay, this is your altitude angle. Altitude angles are basically the concentric circles. Now, all these, okay, before that, all the angles that are mentioned at the periphery or the circumference of the outer circle are your azimuth angle. So these all are your azimuth angles, and your azimuth angles lines also travel radically. These are your azimuth angles. Radical lines are the angles mentioned in the periphery of the outer circle. Okay, so what is azimuth angle? Azimuth angle is basically measured in relation to the north hemisphere or the southern hemisphere, mostly the northern hemisphere. So what do they do is they consider the northernmost here. They consider this angle to be 0, and towards the east it's 90 degrees. Towards the south it's 180 degrees. Towards the west it's 270, and when it comes back again it's 360, or they consider it as 0. So this is the azimuth angle. Next, let's talk about the other lines. So these sunpath lines that curve and they go, they these lines they represent these lines represent the day or month of the year. Okay, and lastly, the lines that cut through, yeah, these lines, they represent the hour of the day. They represent the hour of the day. Okay, so I hope this is clear. Now let's consider an example. Let us try to find the azimuth angle and the altitude angle on a random day of a on a random time. So let's consider from on March 21st. Okay, let's consider in the month of March. On the month of March, at let's say at 9 a.m. So at 9 a.m. So here is where it is, the March, and at 9 a.m. So it's somewhere here. Now draw the a radical line towards the periphery. So this is somewhere at, okay, in the sunpath diagram they could consider south pole to be 0. Okay, but it's usually north pole is considered 0. So but let's see here. This would be, let's say, 62 degrees. So this is your azimuth angle, and let's draw a concentric circle within this line. So let's just say it's somewhere hitting 40 something. So your altitude angle would be, let's say, 42 degrees. So this is how you find the sun's position and the angle of it on a particular day of a particular hour. So, and that's how you use the sun path diagram. So now that the sun path diagram is clear, let's move on to our next topic, which is your horizontal shading device. Okay, before moving to the shading device, let me talk one more thing. So this is your horizon. Your horizon is basically, usually it's zeros. So, and let's say your sun is somewhere here. Okay, let's say this is at 30 degrees. Your zenith is at the top. Okay, at your head basically. So zenith is this, and your zenith angle is this. And usually your zenith angle plus the altitude angle gives you 90 degrees. Okay, so sometimes they might ask you a question. Say, let's say, for example, the altitude angle of a sun is 50 degrees and the azimuth angle is 130 degrees. Then what is the zenith angle of the sun? So here you do not need the azimuth angle at all. You can just basically take this 50 degree and then find your zenith angle. So your zenith angle would be 90 minus 50 is equal to 40 degrees, and this would be your zenith angle. Now let's move on to our horizontal shading device. Your horizontal shading device, your basic sunshade, which is your basic sajja, is also a horizontal shading device. Now let's consider this to be a window. Okay, this is your window, and you have your sajja here. Like your wall extends, and we have to find the length of this horizontal shading device. And the best way to position this or for to find the length or to put your horizontal shading device in such a way that the last ray of sunshade should coincide with the edge of the window. So basically this is how it should fall, your last ray of sun. So the sun ray hitting the window should coincide with the shading device line. And that is the correct horizontal shading device. So we can see it coincides here, the last sun ray. And let's try to find the formula for it. Now, I'm gonna redraw this again. Now let's consider this to be our horizontal line, and this angle to be epsilon. Okay, And we know by the theory of alternate angles in the parallel lines, whatever angle is here would be the same as here. So this again becomes your epsilon. And we need to find the height length of the horizontal shading device, which is your L, and the height of your window is your H, and this epsilon is your vertical shadow angle. Now let's consider tan epsilon. Tan epsilon we know, so tan anything is basically your opposite by adjacent. So you have tan epsilon is equal to H by L. So your L is equal to H by tan epsilon, and this is how you find the length of the horizontal shading device. But what is epsilon, or what is tan epsilon? Let's talk about that now. So tan epsilon can be written as tan gamma by cos delta. So gamma is your altitude angle, and delta is the horizontal shadow angle. And delta can be written as, this can be written as the azimuth angle of the sun minus the azimuth angle of the wall. Now let's move on to our solar heat gain. Solar heat gain is not the same as your general heat gain, because general heat gain can happen through a lot other mediums as well, not just because of the solar radiation. Solar heat gain is basically the heat gain that is the gain heat that you gain basically from the solar radiations alone. So that is your solar heat gain. This is due to solar radiation alone. And the formula is solar heat gain is equal to U value into absorbance of the external surface by surface conductance of the outer surface. So SHG is your solar heat gain. U is the U value of the building component. So this is U value of building component, and A is the absorbance of the external surface. Is the surface conductance of outer surface. So this is your solar heat gain formula, and last thing that we'll talk about is your solid heat in terms of formula I'm talking. So this is solid temperature. Sorry. Solid temperature is the temperature of the surface rather than the air, like the temperature of your wall, like that. So it's basically the surface temperature. And the formula is the surface temperature or solid temperature is equal to the outdoor air temperature plus intensity of solar radiation multiplied by the absorbance of the external surface divided by the surface conductance of the outer surface. So T naught is your outdoor air temperature. I is the intensity of the solar radiation. A is the absorbance of external surface. And SC naught is the surface conductance of the outer surface. So emissivity is basically the ability of a material to radiate or reflect energy. Okay, so the ability of a material to radiate energy is known as emissivity. And so basically, highly reflective surfaces. Highly reflective surfaces have low emissivity and dull surfaces have high emissivity. So what do they usually do is, since glasses are highly reflective materials, they coat it with low emissivity coating so that it radiates energy as much as possible. So basically, if this is your, yeah, okay, this is your glass wall, they coat it with a low emissivity coating. Okay, so this is your glass, this is, so what will happen when the solar radiation hit? A lot of light passes through it, but the heat is radiated or reflected back, like light passes through it, and heat is reflected back. So that's why they coat your glasses with low emissivity coating. Then we have something called as your solar heat gain coefficient. We saw about solar heat gain factor, which is the heat gain that you get due to your solar radiation, and that formula is your U value into absorbance of the external surface by surface conductance of the outer surface. Now the solar heat gain coefficient, which can also be written as SHGC, is basically the solar heat admitted to the building to the total incident solar radiation. It gives you your solar heat gain coefficient. Your solar heat gain coefficient can be written as the solar heat that is admitted to the inside of the building, that is admitted in to the total incident solar radiation. Now, let us consider an example. Let us say out of 100 watt of solar radiation that was incident on a surface, only 40 watt is admitted inside. Then, what is the solar heat gain coefficient of it? So, what do? You basically divide it. So, SHGC is equal to 40 by 100 is equal to 0.4, and SHGC is basically a value between 0 and 1. So this is a value between 0 and 1. So what does the 0.4 here means? It means 40% of the incident solar radiation is transformed into heat. Okay, and so with this thing that we know about, let's consider situations. Let's consider a building in a hot climate. Should the solar heat gain coefficient be higher? No, the solar heat gain coefficient should be lower so that the heat transmitted to the building is lesser. So what I'm trying to say is, your solar heat gain factor coefficient, if it's low, then the thermal transmittance is also low, or solar heat gain transmittance. So in hot and dry climate or hot and humid climate, you want very little amount of heat to be transmitted into the building. So you need to have materials which have solar heat gain coefficient which are lesser. In hot, colder climates, you would need something which has a higher solar heat gain coefficient. Okay. So in hot climates, you would need solar heat gain coefficient to be less, and in colder climates you would need your solar heat gain coefficient to be more. So this is about thermal conduct quantities and terms related to it.